Good morning. In this short video, we briefly want to discuss the analysis of the components of eigenvalues and eigenvectors. In our last video on the concept of eigenvalues and eigenvectors, we discussed and we arrived at an equation of this form, AS equals lambda S, which we assumed to be an equation 1. Here we said A stands for a square matrix, S stands for an eigenvector, and the lambda stands for an eigenvalue. But at this junction, we only discuss A, which is a square matrix, being the component of the concept of eigenvalue and eigenvector. What do we understand by the A? We have said that A is a square matrix. Why do we choose A in the concept of eigenvalues and eigenvector? The answer is there is an inclusion of a determinant when it comes to a characteristics equation of this one, A minus lambda I equals 0. This equation is applicable when a matrix is only given, and you have to determine the eigenvalues and the eigenvector of that matrix. And the inclusion of that determinant shows that only a square matrix can have a determinant. Because a rectangular matrix does not have a determinant, that has been the backbone for the limited inclusion of the square matrix in the study of the eigenvalues and eigenvector. And what is a square matrix? For us to understand a square matrix, we must be able to understand what a matrix is. We all know that a matrix is a rectangular or a square arrangement of elements in a regular part. By the time we look at the sentence, we are going to underline the word rectangular square. That means a matrix is either a rectangular or a square form. When we talk about 2D, and we also talk about the word here, elements, and the fourth one, regular pattern. These are the properties of the matrix. It is either a rectangular shape or a square shape, and another property, it must have elements, which are what? The entries in that what? Rectangular or a square shape, and it must be in a regular pattern. That regular pattern is a particular pattern that follows a row, and column. This is a row, this is a column. That is exactly what a matrix is. And these are elements. These are elements. And a practical example of a matrix is the crate of egg. When we have a crate of egg, you look at the shape. It is a rectangular shape, and the eggs are the elements. And the regular pattern, it forms a row and a column in certain numbers. We have a 6 by 5 matrix because we have 6 rows, 5 columns, or you can invert it to 5 rows, 6 columns. Now we also look at our tablets. You could see it forms a matrix. That is also a rectangular matrix, and sometimes it is a square matrix because you have the same number of rows and the same number of columns when it becomes a square matrix. And being limited to this study, we'll be discussing a matrix in which the number of rows and the number of columns are the same. That is a square matrix for this study. And in addition to that, we also have what we call the full and the sparse matrix. Let's take that shape of the crate of egg as an example. When we all know that we have 30 eggs in a crate. Assuming 3 are taken at random without replacement, we are left with 27. That simply means that that matrix is a full matrix because almost all the elements are there. When we talk about a sparse matrix is a matrix in which almost all the elements are 0. When you relate that with the concrete weight of a crate of eggs, it's assuming you have taken out 26 eggs without replacement. That crate is almost empty. That is called a sparse matrix. Thank you.